The emphasis here will be on small, and here is an example. This is the adjacency matrix, 150 nodes, these 3 subgroups. They are, the first 20 nodes, then the next 15, then the following 10, and here you can probably see them by eye. Edge probability inside is 0.7, and inside is 0.3. Okay? And okay, if you didn't see them before, here it's clearer. Of course, they are not ordered, and the difficulty is in finding them now. Try to stare at it. Will you find them? Okay, and what I want to talk about is 2 things. I want efficient algorithms, and here efficient will mean for me nearly a linear time, that is n square log n, if n is the number of vertices, and I want a provable improvement over spectral methods. There is a standard way of doing this, just take the metrics that I show and compute the SVD, the eigenvalue decomposition. I want to try to improve over that. Okay, and this is the outline. I will start by reviewing spectral methods, and I'll spend a little bit of time on why they fail, and then talk about something beyond that are called nonlinear power iteration, and then how can you do prove theorems about it. There is a paper that is out there that is part of this work, another part will come out at some point. Okay, and in fact I will consider a very simple example. Really simple. A lot can be generalized. So I have a big thing, k nodes here, n nodes here. I want to find these k nodes, and k is much smaller than n. Okay. Okay. Is more or less the statement of the problem clear? I went very quickly over it. But
so there's no assumption on the rest of the graph?
Yeah. No, I'll make all the possible bad assumptions. So here nodes are present with probability q, and here they are present with probability p. Edges are present, and we can talk about relaxing these assumptions, but this is not what I want to focus on. Yeah.
So n squared. I mean, linear, I would expect linear in the number of edges.
Yeah, I want linear in the number of edges.
So m log n more than n squared log n.
So you said n squared.
N square, so n square log n. So here I'm thinking, okay, m log n if you want. As you will see, what we'll talk about is things that take the same times and matrix vector multiplication, where this is the matrix. Okay, so it's really like number of edges.
So are you assuming P into advanced states?
We'll see. Okay, some of the things yes, some no. You can think P of Q constant for simplicity. It's that hard enough.
K is constant for logarithm.
And that's the question, right? Of course. Okay. So let's see what happens. So the right way to think about this is, call G the adjacency matrix, and what is easy to see is that the expectation of G is what? Well, it's P here and Q there. So this is the all one matrix, is all one, and then there is a perturbation this that is P minus Q times, this is the indicator vector over S times its transpose. So this is the expectation. And its variance is, apart from the clique is constant, is Q1 minus Q. So in fact, it's convenient once you look at this to work with a different matrix, that is subtract from the adjacency matrix this part, the background, Q times the all one matrix, and then rescale it. Okay? And then rescale it in such a way that each entry now has variance 1 over n. Right? That's if you think a little bit about it, that's really the natural scaling of this stuff.
So here Q is given?
Also, let's say that is given. We can talk about that also, but let's say for simplicity it's given. So if you think about once you do this normalization, what happens to this matrix? Well, this matrix is very simple. It is a rank 1 matrix that you can think of as the signal. This is this piece, once you rescaled, is a rank 1 sparse matrix, plus another part that has 0 mean, and in fact has IID entries. And I want to think of this as the noise. So I want to think as this problem as I have a rank 1 matrix plus noise, and I want to estimate this rank 1 matrix. Okay? And of course, you can already imagine how you can go about generalizing this. If you have k clusters, this will be a rank k matrix plus noise. So this is a type of random matrices that has been studied in a lot of details in probability theory under the name of low-rank deformation of Wigner matrices. Very precise things are known about the eigenvalues of these and eigenvector of these matrices, and this is the most important, single most important bit of information. And unlike in other estimation problems, like where there is signal and noise, and somehow performances degrade slowly with the signals to noise ratio, here there is an interesting phase transition. Okay? If the signal's noise ratio is below a critical value, and that critical value happens to be equal to 1, if you look at the spectrum of this matrix, or better the spectral density, this is the Wigner law. Okay? So this is the distribution of eigenvalues. All the eigenvalues are going to be between 2 and minus 2, and their distribution follows this Wigner law. All right? Further, if you look at the top eigenvector of this matrix, this is basically orthogonal to the vector that you want to reconstruct. So in this regime, there is basically no use in doing principal component analysis. You can forget about it. Right? If lambda is bigger than 1, things change dramatically. There is one eigenvector that pops out. It's at lambda plus 1 over lambda. Beautiful formula. And it has a positive scalar product with the stuff that you want to reconstruct. So in this regime, if you do principal component analysis, pull the largest eigenvector, this will not get you precisely the community or the vector, the rank 1 matrix that you want to reconstruct it, but will have positive correlation, and you can hope of improving over it. So is this clear? So now, okay. So now the question, this phenomenon is really at the basis and the various generalizations and deformation and bells and whistles, of a large number of algorithms. In the problems of finding clicks in random graph actually dates back to a paper, a very nice paper by Alon, Krivelevich, and Sudakov, where they showed the following, that if k is bigger than sufficiently big constant times square root of n, then you can reconstruct this community correctly. In community detection, it was studied. It's a building block of spectral clustering, etc., etc., etc. Okay. So now the question that I want to ask is really, can we beat this threshold, this spectral threshold? That is, can we find, estimate this vector u when lambda is less than 1. Okay? So if we go back to our original setting, graph setting, this means for p minus q order theta of 1, this means for k smaller than square root of n. So if you look at this setting, really the spectral threshold is at p minus q, that is okay. So this threshold in the graph example turns out to be that threshold turns out to be this, I think. Okay. So can we get below this threshold, either in p minus q order 1 or p minus q smaller? Okay. Now what is the basic intuition? The intuition.
Just to parse that formula, so when k is equal to root n, then essentially p minus q, so you're saying in that case when there's a constant gap between p minus q, you can recover it.
Yeah, so okay, this statement about spectral methods, what it tells you is that if k times p minus q is bigger than square root of n times q 1 minus q, okay, PCA works. If it is smaller, it doesn't. Okay? So along Krivulevich Sudakov, they looked at p equal 1, q equal 1/2. In that case, it gives this threshold. Okay? And they actually proved if k is bigger than a big enough constant. Okay. And why there can be hope? Okay? Why there should be hope? Well, one reason why there should be hope is that this is okay. It's the principal eigenvector of a matrix, but it's a principal eigenvector with a very special structure. First of all, it's non-negative, and second, it's very sparse. Okay, so can we use non-negativity and sparsity to beat this kind of phenomenon? Okay, so this is what I want to try to understand. Okay. And in principle, there should be a huge possibility. Purely from an information theoretic point of view, you can reconstruct it as soon as k is bigger than log n. Okay, so there are various ideas for going beyond the spectral methods. There is a bunch of methods that use convex relaxation. There is idea in sparse PCA that use power iteration, and there is ideas that use graphical model methods like belief propagation, etc. None of these, all of these has very interesting ideas, but none of these has provable improvements over this threshold. And in fact, I must say very little because, for instance, there is this work by Elkanan, Florent, and Chris Moore and others, in which they prove that using a certain belief propagation algorithm in certain classes of sparse graph, you can actually improve over spectral methods.
Yeah. So what do you mean by improvement? That you can correctly identify it under that threshold?
Yeah.
Okay.
Okay. So what is the idea of nonlinear power iteration? The idea is the following. Take the normalized adjacency matrix, hit a vector with it. Ideally, this should correlate with your leading eigenvector, but then somehow use the fact that x, the leading eigenvector is known to be sparse by applying some nonlinear function. So at each iteration, computing the leading eigenvector corresponds to multiply, repeatedly by this adjacency matrix A. Here, what I'm doing is that I'm multiplying by A, and then somehow using some nonlinear function to eliminate the excess noise. And here I want to look at a separable nonlinear function that acts component by component. So this is one example. In fact, I will look at these three examples. For instance, one possible idea could be, I want to look for an eigenvector that is non-negative. So at each iteration, I multiply by A, and instead, unlike in normal power method, I set to 0 all the entries that are negative. Another idea could be, I want to look for a sparse eigenvector. So I multiply by A, and then I keep only all those entries that are above a certain threshold. Or you could decide that you want to use some soft rule. Okay, this I'll skip. So this is something that is present in some form in the literature, for instance, this paper by Wang and Zhang. And here I'll show you some simulation that are in terms of this parameter epsilon, that is the size of the hidden clique or the hidden community. And these are for doing 50 iteration and for a matrix of 1000 by 1000. So this is what. For each point here, I have a grid of values of epsilon and lambda, and for each point, I compute the scalar product between the vector that I want to reconstruct and what I estimate. Okay? So this is lambda, the size, the signal to noise ratio, and this is epsilon, the sparsity, and this is a scale between 0 and 1. So you see that small epsilon is good and large lambda is good. This is the spectral threshold. This is the spectral threshold. So you see that you can do a little bit more, for instance, for very sparse, instances, you can do a little bit more than, the spectral threshold that is 1. You can move a constant below that, at least empirically. Okay? So the upshot here is that, this kind of methods seem empirically to be better than spectral. In fact, they are very much used in practice. Of course, there is a couple of sources of criticism here. First, how do you pick this nonlinear function? And second, can you quantify this improvement? Yeah.
On your previous slide, the truncation method looked like it wasn't working at all. Was that?
Yeah, I think that actually is a glitch in the program. We did the simulation last week, and I still don't believe them. I believe this, and you'll see why. And I don't believe this, but it might. Okay, we'll see. It's not crucial, right? Okay, so now I'll explain a slightly different algorithm and how to predict actually, say things about this kind. Of course, analyzing this kind of algorithms is a nightmare because there is all sorts of dependencies popping out after any number of iterations. I mean, one can do rough stuff, but not very precise asymptotics. Okay, so this is my algorithm. I apply nonlinear function, then I multiply by a, apply nonlinear function. I do one simple modification that is subtracting a memory term. Okay, so this is not whatever in memory term. It's a memory term for which we have an explicit formula. You can find it out. And this explicit formula is basically chosen to cancel the correlation between the estimated time t plus 1 and the estimates at all previous time. So decorrelates this by this. There is magically one specific coefficient that does it. And fixed point of these algorithms can be related to stationary point of cost functions of this form. This is the natural cost function that you would try to optimize from a maximization point of view. For instance, if you want to use positivity, you can use here a regularizer that forces x to be non-negative. If you just minimize this, you get standard PCA. If you do this, you get, and if you do the positive part iteration like this, fixed points are stationary points of this. There is also a graph interpretation that, okay, I will say it quickly. If you look, there is a connection with all this story about graphons, etc. If you look at the t-rate of this is really a weighted sum over graph embeddings over in this graph GI. Okay. For instance, that linear power iteration is essentially counting the number of paths rooted at I in your graph. This is counting not paths but tree, and this with very specific set of weights. Okay. So I think that there is an interesting connection there. So this is the difference between. So this is what we call approximate message passing for a reason that I will not explain. This is the difference between the previous power iteration and this. There is a little improvement. Here there is an improvement, but I don't know whether it is because there was a glitch. So this is, here there is a little improvement. But this is not the crucial thing. The crucial thing here is that now I have a formula to predict the asymptotic behavior of this power iteration. And here by asymptotic, I mean n to infinity as t fixed. So here t is, say, 50. So this is, the prediction. This is a formula that gave me this plot, and this is what simulation gave me. And you see that you get very close phenomena. Here you have some threshold. Here it works a little bit better in theory than in practice. Here better.
So this experiment shows that the theory is much better than experiment.
It's a bit better. If you look at it more closely for larger size, the theory is not much better. They're actually fairly close, especially in the sparse regime. And what we have is that asymptotically they coincide. Okay. So from this, there is explicit formula for these plots here, but I want to pull out a few things that you can learn, for instance, using this formula. Okay? This is, for instance, one thing. Right? So this is in this paper with Yash. If you use this Bayes optimal nonlinearity, you can prove that you can reconstruct the set S for p minus q of order 1 as soon as p minus q is bigger than square root of n q1 minus q over e. Okay? So if you compare with what PCA does, you see that we have beaten principal component phase transition, and we have beaten exactly by factor square root of E. Okay? So this celebrated spectral phase transition seems to have a base analogous, and this base analogous is shifted. In fact, we can wonder what happens if you just use non-negativity. So you want to reconstruct any principal vector that is non-negative. Turns out that this positive part iteration does it as soon as lambda is bigger than 1 over square root of 2. Okay, so the standard PCA phase transition is at signals to noise ratio equal 1. If you know that your principal component is non-negative, it moves to 1 over square root of 2. So square root of 2 better than spectral. Asymptotically, we can prove that if epsilon is above a certain number, that is above 0.5, there is no algorithm that can do better than the base version of this algorithm.
Wait, can I ask something here? So what about the Alan Kurelevich-Sudakov? So they can run their thing several times and get constant times Croton for any constant.
Good point. Okay, so this, you were referring to this?
Yes.
But this is, this is for clicks of sides, clicks that are not clicks, they are for sets that are sides 5% times n. And now P minus Q are very close. If P minus Q are far apart, things are trivial. Now you take P and Q that are within 1 over square root of n. This is the interesting regime. And now I'm telling you that no method can do better than this. Of course, if you are interested in very small things, then this doesn't apply. But yeah.
So this is information theory.
Yeah.
That was my question.
Excellent. Okay, that saves me a question. And this is one more thing. I gave you this kind of optimization principle. This algorithm has fixed point as stationary point of this cost function. This is one case in which we can prove convergence to the minimum of this function. Consider the following. If you know that your eigenvector are non-negative, you might want to maximize the Rayleigh ratio subject to the eigenvector being non-negative. Okay? This is a beautiful, interesting problem. Of course, it's non-convex, so it's difficult. We can prove that within this model, this algorithm actually solves this, the problem, this non-convex problem without probability. Okay, there is an underlying theory beyond all of these. These are not 4 examples, but come from some theorem that implies all of them. Just one conclusion. In the very sparse regime, okay, first of all, arguably for this type of problem, you cannot improve more than theta. Here we improved by constants over spectral method. We went down from, for instance, finding click with lambda equal 1 to finding click with lambda equal 1 over square root of n. Probably you cannot improve more than a constant in polynomial time. There is results by Feige and Kraft-Gamer and by Vidgerson and Mecca that kind of point very strongly at this. So since you cannot improve by constants more than constants, it's important to kind of try to understand very precisely how the constants behave. And this is an open problem since the emphasis here was on open problem. Here, in the special case of clicks, so P equal 1 and Q equal 1/2, we can find the click of sides K equals square root of n over E in nearly linear time in n square log n iteration. I think it's a nice challenge to try to do better. I'll buy you a dinner if you can. Thanks.
Any quick clarifications left, or?
Maybe I think that we should ask the fact that we wouldn't say that this work indicates that the finding even is hard. I think you just use this as an assumption in order to show that others are hard. The Vigdors on Mecca paper is withdrawn. There was some
Okay, but Feige, they have they show.
They assume that hidden click is hard, and then they show from this there's all kind of results. But if you ask Uri Feige what he thinks, I don't think he will commit either.
Okay, I don't know what Uri Feige thinks.
Yeah, but he doesn't even claim that. Right? If this is hard, this is also
No, but don't they have some analysis of linear programming relaxations?
of linear programming.
Yeah. Yeah, so the figures on Mecha was supposedly SDP relaxations. Yeah. So these people are analyzed Sherali-Adams relaxation, and I didn't know that the paper of Wiggerson is bugged, but supposedly they analyzed the Lasserre relaxation. They showed that you cannot do it.
So the approximate message passing, it looks like, I mean, it feels like an iteration of FISTA, for instance.
Yeah, it's similar to many things that appear in convex optimization and don't really, I wasn't ever able to map it precisely into one. And the reason is that here, okay, in this thing there is a very specific choice of, first of all, this function that we use here can be anything, okay? Okay, so now you can take it to be the prox operator of something and then, right? But then in general, this BT in general, there is no precise prescription except that it has to be, I don't know, in some range. Here there is a very precise prescription, and if you don't use that precise prescription, all the asymptotic theory that we use breaks down. And that precise prescription is really, you look at the correlation induced on this, between this object and this object, and basically you find the precise coefficient that cancels those correlations.
But BT is independent of the previous iterations. It's
Yeah,
a formula.
you can think of it as a deterministic quantity if you want.
When you say Bayes, what do you mean?
Okay, so this is this slide that I kind of skipped. You can do, okay, one way to derive this is to write the posterior on the variable given the observation, write this as a graphical model, so it's kind of a Bayesian point of view, and write the belief propagation algorithm for this graphical model, and then, this is, not this is what you get from this belief propagation algorithm for, you do a certain number of approximation of it that should be asymptotically correct.
But you don't use any particular prior.
Yeah, okay, so here the prior for this function that you use, so perhaps you didn't notice here, but this is a logistic, so the,
okay.
Yeah. So, but in general, if you know the prior, you could change the thresholding, and so there is something interesting. This is minimax in some class, of course. Yeah.
So we're eating into the coffee time, so let's take the other clarification questions offline, or you can bring them back up in the discussion, but let's cut back at 3 o'clock.